In this class, we will have a preliminary discussion on different polariscopes possible and their usefulness in getting different photoelastic parameters. So, what you find here? I have a polarizer, I have an analyzer, and I am sending a monochromatic light source, and I have a model which is birefringent, which is loaded. And what you find here? You have the background is still dark, and within the region of the model you find fringe contours. Then what do you find here? One can use a monochromatic light source or white light for illumination. So, what I can do is, instead of monochrome light source, I can also put a white light source. So, what I find here is, when I put a white light, which is nothing but light source of multiple wavelengths, now I find one set of contours are colored, the other two contours that we saw, they still remain black. We will spend some time on looking at this again. We will go to monochrome. And now the question is, I see as two dark bands here, are they same as these other dark bands or not? So, what we will do is, we will now rotate the polarizer and analyzer combination, keeping them crossed, and let us see what happens. So, now I rotate them. So, when I rotate them, what I find is, one set of contours remain stationary, these contours keep changing and they sweep the entire model. And what you have here is, this dotted line show that you have the polarizer, analyzer are rotated, they are kept crossed. So, now I go for a polychromatic light source, and as I said, these are colored. This I have not provided the reason, but this I have already provided. When I rotate the polarizer analyzer, you have this as a black contour. It is independent of wavelength. So, what you have here is, in a plane polariscope, it is very clear now, one observes two contours, namely isochromatics, which show contours of difference in principal stress, and isoclinics, they are nothing but contours of principal stress direction. Look at what way we can represent. What I do is, I rotate the polarizer analyzer crossed combination in steps of 10 degrees. One can record isoclinics in steps of 10 degrees and plot them. And what you have here is, what is shown here is, I have an isoclinic here which is labeled as 10 degree isoclinic, and what you find here is, sigma 1 and sigma 2 can have different magnitudes, but their orientation remain constant in this isoclinic, and if I go to a 20 degree isoclinic, the angle becomes 20 degrees, and this you have to extract data by several different positions of the polarizer analyzer combination. You do not see this information available in one experimental exposure. These are the isochromatics, and what you have here is, the direction may be different, but the difference of sigma 1 minus sigma 2 will remain same on a isochromatic contour. So, that is the only difference. direction will not remain same here, direction will keep changing from point to point, but the difference of sigma 1 minus sigma 2 will remain same. In a plane polariscope, what we did, I have the source of light which is monochromatic, I have the first optical element as polarizer, then I have a loaded model, then I have the analyzer. And when you see the screen, you see two sets of fringe pattern. So, one observes two contours, namely isochromatics, which represent contours of difference in principal stresses, and isoclinics, which represent contours of principal stress orientation. So, now what we do, we go and look at what is the circular polariscope. In a circular polariscope, I am going to have two additional elements, and what is the advantage of those two additional elements? The two additional elements serve the purpose of removing the isoclinics. So, what I have here is, I have a light source, I have a polarizer, I have a quarter wave plate, I have the model, then I have the second quarter wave plate, then I have the analyzer. Suppose I keep the analyzer horizontal, the quarter wave plates are crossed, you also have the polarizer analyzer crossed, and I see a dark field. Let us see a commercial polariscope now. This is a commercially available polariscope. This has a light source, and what you have is a monochromatic light impinging on the model. You have the first optical element, namely the polarizer. You have the second optical element, which is the first quarter wave plate. Then you have the loading frame. In the loading frame, you have the model loaded. Here you have a circular disc under diametral compression. Then after the model, you have the second quarter wave plate, and finally you have the analyzer. The advantage of a sheet polarizer is, you have a very large field of the order of 300 millimeters in dia, and they can be easily rotated by a simple mechanism. And what you see in the polariscope is the fringe patterns in dark field for a circular disc under diametral compression. The fringes have to be labeled as 0, 1, 2, 3, etc. This shows the loading frame, how the model is loaded, and what you have is a hydraulic cylinder which is controlled by a pump. By selecting the valve position appropriately, it is possible to change from tension to compression. And what I have here is a load cell which measures the load, and you have the model placed between two horizontal platens, and the disc is kept under diametral compression. This shows the load that is applied, and this reads it in kilogram force. See, the basic optical arrangement of the polariscope is in dark field. So, what we will have is polarizer, analyzer are crossed, first quarter wave plate and second quarter wave plate are crossed. When you have both the pairs are crossed, you will essentially see a dark field. Suppose I rotate the analyzer and keep it at 90 degrees, then what I will have is polarizer analyzer are parallel, I will essentially see a bright field. Rotate the analyzer now. So, what you now see is, you see the bright field fringes. All the elements in the polariscope can also be rotated by this knob, and what you do this, you use this for making this polariscope to function as a plane polariscope. In this, what you do is, you keep the quarter wave plate axis along the polarizer, so you optically cancel the first quarter wave plate. Similarly, optically cancel the second quarter wave plate. Now, the polarizer and analyzer are kept crossed, and they can be rotated to find out the isoclinics in a plane polariscope. Rotate the knob. You can now see all the elements are rotated appropriately. So, you can use this for plane polariscope as well as for circular polariscope.